Perfect. Just going to quickly set a timer so don't go too much over time.
Yeah, go ahead. Yeah. So yeah, we are 5 minutes late. Yeah.
Yeah. All right, so thank you everyone for the invitation to allow me to speak today. I'm going to present the work I've been doing together with David Fajman here at the University of Vienna on the blurb of FLRW space waves on FLRW spacetimes as part of my master thesis. So just as a quick outline, I'll give a quick recap on physical relevance and the general setting on FLRW spacetimes, although of course Zoe Wyatt already gave that to an extent, thankfully enough, yesterday. Then I'll quickly introduce our setting since it's not 100% standard for the FLRW case. Take a quick detour into general results regarding nonlinear stability of Big Bang formation on FLRW spacetimes and how that relates to our results. Then I'll introduce our results and go through the individual proof steps to finally give an outlook on where we're going to go from there. So again, I'll try not to repeat too much, but on a large scale, we assume and perceive the universe to be spatially homogeneous and isotropic up to small perturbations. Again, the well-known picture of the cosmic microwave background is a strong indication that this is a very fair cosmological assumption, and also the way that superclusters are spread out throughout the universe as a whole is also more or less consistent with this assumption. Purely from this, Robertson-Walker proved all the way back in the 50s or 60s, I believe, that this already forces the metrics to be FLRW metrics, so that we have some time on the one hand, on the other hand, spatial time expanding of three-dimensional manifold of constant sectional curvature. So either flat surface, sphere, or hyperboloid sheet. The question one has, of course, okay, we perceive now the universe is roughly consistent with an FLRW picture on large scales. Back with the cosmic microwave background, we perceive something similar-ish up to small perturbations. So the question is, does that work all the way back towards the Big Bang, or was there some other universe close to the Big Bang that then just happened to fall into something close to FLRW spacetimes? So the more mathematical question to that is the Big Bang formation non-linearly stable with the FLRW background or near FLRW background? And the first step towards this is to study the behavior of waves as a toy model for the linearization of this perturbation. Moving on to our setting, we precisely look at four-dimensional spacetime with signified R component for the time and a compact three-dimensional manifold without boundary for space, and then look at something which looks precisely like an FLRW spacetime with this Riemannian metric G bar. And we look at the expansion rate for the case of cosmological constant 0, so t to the power 4/3 gamma, with gamma between 2/3 and 2. I'll comment in a second on those two boundaries. And then we look at solutions to the wave equation on these spacetimes. The one point where we aren't, strictly speaking, FLRW spacetimes, but something more general is, again, that we aren't assuming that this metric or that the space we're looking at is of constant sectional curvature. Of course, every case of that type is contained here, but we realized while we were working on the proof that it was completely irrelevant, besides maybe some slight nicer constants, that we assume constant sectional curvature. So we just dropped it in the proof and look at this mathematically more general case, although the physically relevant cases are just the classical FLRW spacetimes, as far as I'm aware. And again, the comment on the edge cases, in the case of gamma equals 2, we are in the Einstein-Stiff universe. So if this basically models the expansion of a massless ideal fluid universe, then in this massless ideal fluid, the speed of the sound is the speed of light. And on the lower bound for gamma, this corresponds precisely to the Milne universe. And we expect that to be a special case because the Riemannian curvature tensor simply doesn't blow up in the space in the Milne universe. So we also don't expect any kind of wave blow up along similar veins. To a quick detour on what general results on linear and nonlinear stabilities over this background are. Speck proved in one paper on its own and one together with Dotniansky back in 2018. On the one hand, that the Einstein scalar field system is globally nonlinearly stable over spaces of positive curvature with regards to this near FLRW background. And on the other hand, for the flat case, we also have a result for the stiff case that we absolutely can't quite handle. But the moral of the story is one has results for certain types of curvature or certain types of expansion, but not in our more general setting. So then in the same year, Franzen et al. Looked at what is basically our setting. So again, the expansion rate t to the power 4/3 gamma. And excluding the Swift case and excluding the Milne universe, and then looked at the blurb of waves within the flat FLRW spacetimes as the specific restriction, was we then look at the more general class. And they proved a general blurb result, which roughly sketched and is also along similar veins what we then managed to prove in more generality. They proved that the blurb would be of the form of basically when the waves go back towards the Big Bang, the waves roughly look like some smooth prefactor times t to the power 1 minus 2 over gamma. I'll remark in a second on where this comes from, but that's basically the idea. And the one point where they used the nicety of being in Euclidean space essentially is that it allowed a lot of that this allowed them to commute any spatial derivative with the wave operator, simply because all spatial derivatives commute. So a lot of technical estimates became significantly easier, and in particular, it was fairly easy to use any energy estimate on the wave to any derivative of the wave, and thus gets the regularity of the leading coefficient fairly easily. For our setting, we're going to need some kind of replacement for that, obviously, since we can't commute derivatives. However, this comes very naturally when we look at what the wave operator actually is in our general setting. Namely, it is this kind of splitting into time derivatives up to order 2 and a scaled spatial Laplacian, where the Laplacian, I really denote the Laplacian on this space m bar, which is in no way adapted to the expansion. This power t to the power 4 over 3 gamma, this factor in front, is precisely from the expansion of the space in our spacetime. In particular, this Laplacian is completely time independent, so we can just commute this Laplacian with a time derivative acting on a scalar wave. So we can, instead of having individual derivatives commuting with the wave operator, we now just have the Laplacian commuting with the wave operator, since, of course, the Laplacian also commutes with itself, and it doesn't act on any time prefactor at all. And this basically is the replacement we have to make, and then try to go through the argument in total. Second remark, what one can see from this simple expression is precisely why we expect this blurb rate of 1 minus 2 over gamma when we go towards the Big Bang, which is that if we look at the spatially homogeneous solution, so when the Laplacian becomes 0, this really just reduces to an ODE of second order in time. And one that is even very trivially solvable precisely by t to the power 1 minus 2 over gamma. So one expect in this case that any blurb will be similar to this spatially homogeneous solution unless something really weird were going on. And that is precisely what we proved. Vaguely stated, I'll go into more specifics during the rest of the talk. Our result is that when we follow waves back towards the Big Bang, we precisely have the same asymptotic expression as Franz-Nadal proved in the Euclidean case, that we have a smooth leading coefficient A times this spatially homogeneous solution plus some higher order terms. And that if we give some initial conditions on the initial data at some slice t0, that we can also actually prove that we have precisely this rate of blurb towards the Big Bang. Of course, for example, the 0 function would also technically be a wave, but doesn't experience blurb, obviously. So we do need some kind of additional requirements. Good. The main technical ingredient, what we used, which is to an extent in a way almost similar in model to what we just had in the K-estimates for Schwarzschild spacetimes, was that we need some kind of energy that we have to control. In particular, we used the energy that is the most intuitive when we compare to the standard wave equation in, like, not even spacetime, just as one would do in the standard PDE course, where the L2 norm of the time derivative and the L2 norm of the spatial derivative is actually truly conserved. In our case, we look at the L2 norm of the time derivative of a wave and the L2 norm of the gradient rescaled by the expansion rate. So basically this is just the homogeneous H1 norm on our spacetime, only that we integrate this entire thing not over some adapted surface, but really over just the spatial manifold without any further adaptation. Exactly. Again, comparing this energy and inserting what we expect to be the blurb order. In this spatial part would obviously vanish, and here one would have something of the order t to the minus 4 over gamma. So one would expect that when one rescales it for what we expect to be the blurb rate, that this would stay bounded, and this is precisely what we prove. That we can, from our initial data set at some point of time t0, comparing backwards, we can control with this rescaled energy, any rescaled energy at earlier times. And the same type of estimate holds when we rescale the energy by what we suspect to be the leading coefficient, only that, of course, we have to adapt the order a bit. The basic idea here is really just a Grunwald estimate, which is fairly easily calculable. We really just use the closest of the manifold to integrate by parts and the form of the wave equation. Although there is another proof that was done in Franzen et al., which we could also adapt here, similarly using energy flux methods. Next, again, we use the idea that we can just commute the Laplacian and the wave operator, that we can just generalize any estimate we got on our wave to any Laplacian of the wave. So we really get something that looks like very high somewhat of regularity, just that we're skipping a lot of derivative orders and thus we run some technical issues. But the basic moral idea is that we can, with these energies, bound very high order derivatives of both our wave and our wave rescaled by what we suspect to be the leading order. With these technical estimates already in the bag, we can now move on to the first step of the blurb result, namely that this leading coefficient A actually exists, that then also is leading order immediately follows from the energy estimates, and that when we take the difference, then we actually do have a convergence in this rescaled energy, which really proves that we have strictly this leading order A times our homogeneous solution plus something of higher order, which by comparison vanishes at least. The proof itself is lots of half technical. The basic idea is that using the energy estimates from earlier on the rescaled wave, we can prove that in particular, the time derivative of this rescaled wave is something that is integrable in an L1 sense. And then one can just use the fundamental theorem of calculus to extend our rescaled wave from T0 all the way back to the Big Bang. Again, just fundamental theorem of calculus. And we just copy and copy this procedure for any order Laplacian. So we have a lot and a lot and a lot of limits. And we have to show that these limits are consistent to then obtain smoothness. And this is really just some subtle of machinery that's rather tedious to calculate through. The basic idea and real key technical ingredient is that on closed manifolds, as we had before, the Laplacian is an elliptic operator in space. And with that, one can just get a lot of very clean subtle estimations. And yeah, that is really essentially the basic idea. And this is where we really keenly need the closeness. Without it, this wouldn't quite work. Finally, we have to give some conditions, as mentioned before, on that this is actually the leading order of blurb. I have the precise formulation on the final slide if anyone's interested, but morally, we have to require three things, or it's sufficient to require three things, to be more precise. Number one, that at where we take our initial data, the time derivative is not identical to zero. This is more or less to just exclude stuff like constant solutions or zeros. Secondly, that the point at which we take our initial data is small enough compared to the blurb rate. Essentially, this is that a certain prefactor is non-negative, and this is a relation of some constant dependent only on gamma times an exponent of T0. And actually satisfying the smallness becomes significantly harder the more we move towards both our edge cases. So the method we have right now can't quite cover these edge cases of the stiff universe and the Milne universe. Third condition is that, which basically already contains the first in a way, but this makes it slightly more specific, is that the L2 norm of our time derivative must in some sufficient way control both the L2 norm of its own Laplacian and up to 3 derivatives of spatial L2-data. So even slightly more generally, we have to control up to 3 derivatives in both space and time in an L2 sense with the first time derivative in an L2 sense. And if all of these 3 things are satisfied, then we prove that, then we can prove that the L2 norm of our leading coefficient over space doesn't vanish, well, it's strictly positive, and thus by continuity, or just in general, we have that globally, we have some kind of blurb of strictly this leading order 1 minus 2 over gamma. Finally, since of course, for, well, applications, so to speak, and actually being able to check these kind of conditions, having data on the entire manifold isn't particularly useful. One would be interested in whether one can require some kind, to get some similar conditions for local data. This is currently still a work in progress on my end. The basic technical difficulty is that a lot of this global blurb results use integration by parts and in an energy flux method that I mentioned before in passing. And if we go to some kind of smaller domain, we get first order derivatives, which of course by the entire way we structured up this proof, we've always skipped so far. We always went from zero derivatives to the Laplacian spatial derivatives and so on and so forth. So we need to get some kind of way of controlling some first order derivatives. But we highly expect that very similar conditions can be set on a local set to then give some kind of local verb. Maybe these might be a little cleaner when we go to strictly spaces of constant sectional curvature. Where can one go from there? As I mentioned before, the entire end goal to an extent is that we can then attack nonlinear stability just with this intuition in mind of what happens with linear perturbations, considering this toy case. And in particular, the interesting case is negatively curved spatial manifolds, simply because we just don't know anything there, or know the least there, more precisely. Another way that we can go with this is, again, that just using this to the Milne universe probably won't yield too great results if we consider the massless case, because again, the Riemann curvature tensor just doesn't blow up, so we don't expect anything to happen. But we do suspect that if we add some kind of matter fields to this entire universe, that this may be able to then actually still generate a type of plurbs, and so we are considering throwing this entire procedure essentially to the Milne universe with some matter field added. And finally, we are also considering applying this to other types of equations. Again, we had this in the talk previously, that there are some conservation laws in the Einstein-Plateau system, and whether this entire idea of using conservation laws to then generate smoothness and stability results, if it can be applied to other equations, is of course of interest, and we will consider looking into that. All right, that's it for me. Thank you for listening, and I'm open to questions.
Thank you very much. Thank you very much for a very clear presentation. So, questions?
Do you know anything about what's happening in the expanding direction?
So you mean with positive cosmological constant, or
no, time going, because
with future
going to zero.
I know of the Milne universe case that we have proved that there is a pseudo nonlinear stability that I think both David and someone else's name says me proved that kind of stability result. I don't know future stability in our setting necessarily. Maybe David knows more on that than I do.
Well, I would suspect they're all stable to the future, but I'll think about this and tell you, Piotr, in next week.
So one way of trying to get a nonlinear model out of this would be to allow the metric to depend upon time slightly, because that's what, well of course, if you're in the blow-up regime, then and the metric depends upon the fields, the dependence will not be slight. But I imagine that in this energy method, there is room, right, for a slight or for some time dependence. Maybe it would be interesting to see how bad it can go.
I think that there is quite a lot of room for energy dependence, because again, looking at like the thing that really drives the blow up in our case is this time derivative part. The spatial part is basically just a technical nuisance for the energy conservation. So given if we have at least something similar to this to this wave operator expansion, maybe up to some additional perturbations, given that, I very strongly assume that one could then expand this, because again, the time derivative is really the only thing one has to control effectively.
Maybe even if you had some terms which blow up in the metric, but at a slower rate than this conformal factor, then
we can see by comparing the rate. The one point where that might be a little bit of a difficulty is that precisely in this rescaled energy, that is where the blurb rate of the energy is precisely this spatial coefficient. So one has to be a bit careful maybe expanding there, because that's right on the edge of still working essentially. But I think that with that, adding time perturbation into the metric should, with a little more work, lead to a great result, like just intuitively.
Okay, thank you. Thank you all three speakers of these sessions. I think we should take a 5-minute break. So let's meet again at 3:10.